Greetings from Istanbul Technical University. I am Kerem, the team lead of IT Rover Team. We proudly present our 10th generation rover, IT Rover. We are ready for the University Rover Challenge 2026.
Our T-slot aluminum chassis consists of a mainframe and a center column. The rover fits into a 1.1 meter cube and provides a 0.3 ground clearance. For optimal terrain adaptability, we utilize a rocker suspension paired with a differential bar. This linkage effectively maximizing chassis stability over obstacles. Finally, our 3D TPU printed airless wheels are driven by brushless DC motors, which feature integrated bearing housings for reliable protection against external factors.
Powered by a 42 voltage BMS managed battery, our electronic box acts as the rover's central nervous system. Our custom PDB uses self-designed buck converters to provide stable 24, 19.5, 12 and 5 voltage rails, ensuring consistent delivery to all subsystems. The system includes an emergency hard kill switch that immediately shuts down all power.
The chassis electronics box functions as the central nervous system of the rover. It's composed of a custom-developed vehicle control unit and an embedded computer in a local area network that together drive other subsystems, including but not limited to the mechanical arm, the science system, the LiDAR and the drivetrain. The new generation VCU also handles persistent status and error logging on flash memory.
To improve our situational awareness during the mission, we built our own quadcopter drone based on a DJI F450 frame. It carries onboard electronics and a real-time camera that scans the environment and assists both the pilot with piloting and the rover with the delivery task. Powered by 4 brushless motors as expected from a quadcopter frame, the drone can stably take off and operate while carrying its payload.
Our communication system uses 2.4 GHz RF modules to transmit both high bandwidth video and telemetry data. H.265 encoding cuts camera feed bandwidth while hardware accelerations ensures ultra-low latency. A dedicated interface handles video streaming and a secondary UI provides real-time mapping and precise rover positioning.
We engineered a 6 degrees of freedom robotic arm driven by custom servers with integrated BLDC motors for maximum power density. By synchronizing a belt drive transmission with our tailored cyclotron reducers, we achieved high torque to weight ratios with near zero backlash. The implementation of carbon fiber and aluminum minimizes inertia, enabling the high dexterity and effector to perform precision omnidirectional maneuvers in dynamic environments.
ROS processes sensor data for both real-world operation and simulation in gazebo. Movable performs numerical forward and inverse kinematics, allowing the end effector to execute control panel manipulation tasks. Based on the computed kinematic solutions, the end effector autonomously reaches target positions identified by a YOLO model. Additionally, Cartesian control via movable servo ensures smooth and responsive motion during task execution.
The rover achieves precise localization by fusing GNSS and IMU data, enhanced by a dual antenna heading setup. Perception uses LiDAR point clouds and coast maps for obstacle avoidance with a camera supporting search tasks. Determined objects detection combines a YOLO model with probabilistic search, while a spiral pattern enables long-range architect detection. Sunlight-readable triple status lets provide real-time system feedback.
Our science payload integrates 3 primary units: drill, digger and analysis systems. The digger utilizes a custom shovel with an integrated peristaltic pump for teleoperated soil acquisition. To ensure analytical precision, the sample is homogenized with a liquid medium and filtered to mitigate cross-contamination. For subsurface exploration, the drill retrieves samples from depths up to 15 centimeters, ensuring secure material transfer and delivery with minimal loss.
By applying a geophysical method for the first time, we have integrated a newly developed magnetometer system onto our rover. To conduct magnetic mapping across the survey area, we utilize a 3-axis magnetometer performing measurements that generate a high-resolution map of the region. This approach enables us to better understand subsurface characteristics and interpret structural elements such as faults, lineaments, and lithological boundaries.
Our rover's scientific payload uses a depth camera to establish scale and coordinal orientation for analyzing stratigraphic profiles. The high-resolution camera then captures distinct geomorphological features of the site, allowing us to reconstruct the depositional environment and geological history. Environmental conditions are monitored via onboard sensor tracking temperature, humidity, and atmospheric gases.
Newly designed nanoparticle-based detection system will enable identification of biosignatures. Glucose will be quantified by RGB analysis, while riboflavin, ATP, and nucleic acids will be measured spectrometrically. In parallel, the non-hydrogen test will detect free amino groups. Results will be cross-validated using the breadth-for assay to verify the biotic nature of the sample samples and increase reliability.
Thanks to our UV spectrometer, we examine our biosignatures quantitatively. Our priority for design of Raman spectrometer is to eliminate optical background. Besides our 785 nanometer laser diode preference, photo bleaching method and fast Fourier transform are applied for reducing fluorescence.